And we'll go from current slide. And I'll make the last announcement. I made it before. Contrary to what's been the pattern so far this term, I will have office hours on Friday morning. Well, some, not very many, because we have a meeting scheduled for 8:30, but we have to be there by 8:15. So I have office hours from 7:45 to 8:15, a full half hour, and then I don't know what time the meeting will be over. It's hard to say. It won't, I guarantee you won't be over, it'll be at least an hour. So if it starts at 8:30, I won't be back in the office probably any time before 9:45, okay, because it's in a different building. And it may be later, but whenever I get out of the meeting, I'll be back in the office until 11:45, and probably later. But this is a mandatory meeting. We have to be there, so sorry. I know I'll be out of the office from 8:15 till probably 9:45, and maybe longer, but okay. So I did want to let you know that. All right. Any questions on anything we've done so far? Okay. We're on the top of page 184, Chapter 3, Applications of Differentiation. We're in Section 3.3, Increasing and Decreasing Function, and the first derivative test. And we did the first derivative test last time, and example 2 is the application of that, the example of the first derivative test. And it says here, find the relative extrema of f of x is equal to 1/2 x minus sine x on the interval 0 to 2 pi. How in the world are we going to do that?
Very carefully.
Okay. And what's the good answer? What's your first step? Take a derivative. Okay, and what will that be? Whoops, let me get my pen set up. Okay, say again. I can't hear you. Oh, who cares about the projector? Just need to see what I'm doing. Y'all don't need to see it. What's wrong with you? You think you're special or something? Okay. Of course you are. Oh, I'm recording this. Oh, yeah. Okay. F prime of x is what? One half.
Well, I get cosine.
Yeah, minus cosine x. There it is. Pretty easy derivative to take. Now, why did we take a derivative anyway?
So that we can plug in our intervals and see what it's doing, see if it's negative or positive.
Okay. Yeah, ultimately we'll do that. But first we got to do what? Find them. Find those relative extrema. That's what the question asks for. Okay? And then we'll find out positive, negative, that's the kind of stuff to tell which they are. First we got to find them. So how do we find them? Why do we take a first derivative?
We can set it equal to 0.
Okay. The relative extrema are where the first derivative are either
0 or undefined.
0 or undefined. These polynomial function combined with a sine or cosine function, they're defined everywhere. So there's not going to be any undefined. So it's just going to be where it's set equal to 0. Okay? And then what do we do to figure out what that is? What value x will make that statement true? How do we do that?
Cosine is 0 at...
Okay, now it's 1/2 minus cosine x equals 0. So one good thing would be to add cosine x to both sides. And that would give us, I'm going to reverse sides on you, cosine x equal to 1/2. right? Now the question is, what values of x between 0 and 2 pi will give you a cosine x equal to 1/2? Hey. I'm sorry? Okay, which test is that?
The second one. I didn't get it last week.
Oh, you mean for this?
Mm-hmm.
Yeah, for calculus?
Yes, sir.
Okay, sorry.
Thank you. Well, I'll give it to you Monday.
Okay.
I gotta go. I'm late for my doctor.
Oh, okay.
Thank you.
All righty.
Is that pi over 6?
Yeah. Just a moment here.
Pi over
Yeah, I remember her name.
3. I didn't know she was in it.
Huh?
I don't think she was in this class.
No, I said calculus. And she said yes. I just gave her a calculus class test. I don't think she's in here. That's why I asked her. I said, this class? And she said yes.
She messed up.
It's so sad that we have so many students who come so infrequently. I know I've seen her before, but in class, I'm sure, but I can't remember which one.
They should make they should really make
What's that?
They should make attendance mandatory.
Yeah, well, there's
I've
rules
wondered why
about
they
that.
don't do that.
Huh? Yeah, we used to do that when we were at Western State Technical College, and the state got all over us.
Why?
Well, they said if a student can master the material without being there, why should he be punished and made to go there? Or something. I don't know. I'm not high enough up to hear the arguments, but that's basically what we...
And, I mean, one thing that gets me, and it was like this at UAP too, but people coming in late. It's like it's just like interrupts the train of thought, interrupts everything. You know, I mean,
Yeah.
none of them lock the door.
Just like that, you know, but I think, but I mean, I swear, I'm picturing, I don't think that's Tyler, is it? Yeah, she's that over there. I know it's not Diamond, it's not Nakoma, it's not Kenesha or Brittany. It could be Brittany. I may be thinking of a different, that may be Brittany Walker. Yeah, that's it. When I looked at Brittany before, I thought, I have two Brittany's in another class, and I was picturing them, but this is probably the Brittany in this class. Sorry, I shouldn't be recording this. But anyway, back to cosine x equal to 1/2, somewhere on the interval 0 to 2 pi.
That's pi over 3.
Pi over 3 is one place, it certainly is. So x is equal to pi thirds. Is there any other place?
It would be, I try to go all the way around there.
Yeah.
Is it, see, the bottom is 3 over 2 pi. So the next one would be, to the 9 over 6. Is it 11 over 6?
No, it's not over 6, and it's not 11, but you're thinking right, but here's sort of an easy way to do this, okay? Or at least I found it easy. It may not be for you. Picture your unit circle, okay? I haven't drawn it yet, but sort of picture it, and I'm going to try to make it as close to a circle as I can. It's not a very good one. Now first, where is cosine positive? First and fourth, okay? So, not over there at all, okay? Cosine's negative over there. So, where is it 1/2? Well, that's where the adjacent is 1/2 and the hypotenuse is 1. So if that's a unit circle, That's going to be up here, and sure enough, that's pi thirds. Okay? Well, then it would have to be down here, equivalent here. I didn't draw it very well. Yeah, the mirror. So it's pi thirds short of, that's your reference angle, of 2 pi, right? Okay? And 2 pi is how many thirds? 6 thirds. So 1 short of that would be 5 thirds. Okay. So the other would be 5 thirds pi. Now that's how I think of it. You might not find that helpful, but that's how I do it. Okay. So those are the 2 places where the first derivative is 0. I'm going to erase my graphic here if that's okay. Woo, not everything. All right, to erase that because it's right in the middle of where I'm going to work. This part. Okay, all right. Okay. Okay. So we found the 2 places where the first derivative is 0. Those are your extrema. Well, wait, we don't know that for sure either, do we? Because you may have a first derivative being 0 with it not being an extrema. So now what we have to do is split this interval, and I'm going to draw it this way this time. Cosine is 1 at 0, is 0 at pi halves, is negative 1 at pi, is 0 at 3 halves pi, and back at 1 at 2 pi. Now, we're not counting 0 or 2 pi. Those are parentheses there, so it's not there. So here, okay. Now, why did I draw cosine? I'm not sure. Okay. I'm just showing you, well, this is where there's your 1/3 pi and there's your 5/3 pi right here. That had nothing to do with this. Sorry about that. I was drawing the wrong one. So let me erase that one too. I was stuck in the wrong thinking there. Sorry about that. But it's another way to look at it. What we're needing to draw is that function. Okay? And we're doing this between 0 and 2 pi. Okay? Now I'm not going to draw the function, but I'm going to use those same kind of data points there. Now we're doing it the function here, not the other. So basically what we're doing is picking a point, and let's see, here was our pi thirds, okay, and here was our 5 pi thirds, approximately, okay. This is pi, this is pi halves, and this is 3 halves pi. Okay. Yeah. Just to give us references. So we need to pick some points. And actually you could do this either way. Now I wish I had, well, here, just around. Okay. We're doing example 2, top of page 184. Okay? Now, there's 2 ways you can approach this. Okay? I didn't think about this. I should have. I went back to the function. I was going to look at values there, but in order to do that, you need to know the value here too, you know, at these 2 places. And then see which is the relative max and min. But as Clark said earlier, I wasn't really focusing on it yet, but all you have to do is get the sign of the derivative at various places. We know the derivative is 0 here and 0 there, right? What we want to know is what the derivative is somewhere on this side, on that side, on this side, and on that side. And we really don't care the value of the derivative. We want to know the sign of the derivative. So, pick you some test points. We know it can't have another change because it's a smooth continuous function. It cannot have another change here or there. You know, it's got to be here. So, and here's Harrison. And here's 95. All right. We're doing example 2, top of page 184 in chapter 3, application of differentiation, section 3.3, increasing and decreasing functions, and the first derivative test. Now, what we've done so far is they gave us f of x. It says find the relative extrema on this interval from 0 to 2 pi. Okay? Now, f of x is a smooth continuous function made up of a polynomial function, which is smooth and continuous, and a sine or a cosine, which is smooth and continuous. So this one's going to be smooth and continuous. So we won't have any places where the first derivative is not defined. So all we're interested in is where the first derivative is 0. So that's what we did in the first step, and we found these are the two values where the first derivative is 0. Now all we have to do now is pick two values, and we can do it one of two ways. Pick values to the left and to right of each of these two zeros and see what the sign of the first derivative is. Is it positive or negative? That lets you know whether it's increasing or decreasing either side of the 0. Okay? And the other way you could have done it was to get the value of f of x, not the derivative, f of x at these 2 points, and then see which one, what's happening on either side of that. Okay? So I think it is, as Clark I think was suggesting, let's look at the signs of these. We know it's 0 here and there. Oh, there. Okay? We know those are our two zeros. So pick a point to the left of pi thirds. Pi over 4 would certainly work. So let's do f prime of pi fourths. And that would be 1/2 minus cosine of pi fourths. And what is the cosine of pi fourths? I hear head scratching going on. Okay. It's cosine of pi fourths. Anyone remember? Root 2 over 2. Okay, now all we're interested in, we're not really interested in the value, we're interested in the sign. So the question is, which is the larger of these two numbers? 1/2 or root 2 over 2? Well, since they have the same denominators, the question is, which is larger, 1 or root 2? Root 2 is, because root 2 is 1.414. So this is larger. With the minus sign, this is negative. So here, at pi fourths, your first derivative is negative. Okay? Pick a value to the right of pi thirds. Pi over 2 looks like a pretty good one. Okay? So let's do f prime of pi halves. And that's going to be 1/2 minus the cosine of pi halves. And what is the cosine of pi halves? One. No, I don't think so. Sine of pi halves is 1.
Oh, 0.
0. Okay. 0. Okay. So that makes 1/2 minus 0. What's its sign? Positive. Okay? So what does a negative first derivative tell you here? Negative first derivative. The name of the section. 3.3. Increasing and decreasing functions. So I ask again, what does a negative first derivative tell you? Decreasing function. It's decreasing coming up to pi thirds. It's 0 at pi thirds, and then it's positive after that, so increasing. So what does that make pi thirds? a relative minimum. Okay? So this is your relative minimum. Okay? So let's move over to 5 pi thirds. Pick me a point to the left of 5 pi thirds. 3 pi over 2 looks like a good candidate. And what is the f prime of 3 pi halves? That would be 1/2 minus the cosine of 3 halves pi. Anyone know what the cosine of 3 halves pi is? Zero. Okay? So 1/2 minus 0, I even know the value of that one. 1/2, and it's positive. That's what we're interested in. So the first derivative is positive here. We know it's 0 at 5 thirds pi, because that's what we did to begin with. So pick me a point to the right of 5 pi over 3. 2 pi. Why not 2 pi? It should be fine. What is the value of cosine at 2 pi? I've got room, I'm just too lazy to write. F prime of 2 pi, that would be 1/2 minus cosine of 2 pi. What is cosine of 2 pi? Yeah, okay, good guess. Multiple choice, okay. Yeah, because sine is 0 at 2 pi, cosine is 1. Cosine starts at 1, so it ends up at 1, okay? And 1/2 minus 1 is? Negative 1/2. That's what we're more interested in. It's negative over here. So what does the positive first derivative tell us? It's an increasing function to the left of pi thirds, and it's 0 at pi thirds, and it's decreasing to the right. So what is it? Relative maximum. Now, okay, remember this, okay? Just because the first derivative is 0 doesn't guarantee in its extreme. You could have something come up to a value, be a first derivative of 0, and then go up like that. That's neither a minimum or maximum, okay? So just because the first derivative is 0 doesn't guarantee you have a relative extreme of there, okay? Relative extreme there, okay? So you do have to check either the values on either side or check the first derivative on either side. Either one of those will do it. Okay? So that's what we got. Let's see what they got out of it. All right for me to erase mine? Okay? So let's see what they do. Note that f is continuous. How do we know that? Made up of a polynomial function and sine function. Both of them are continuous, so it's got to be continuous. Not only is it continuous, it's smooth, because both of them are smooth. So therefore, the first derivative will always be real. I mean, there will be a value for it. And the first derivative is 1/2 minus cosine x, which you see is also smooth and continuous. Okay? Set that equal to determine the critical numbers. That's what we call these, where the first derivative is 0 or undefined. On this interval, we set f prime equal to 0. When you do that, 1/2 minus cosine x equal to 0. Solve first for cosine x equal to 1/2, then solve for x. X is equal to pi thirds or 5 pi thirds. Just like what we got, those are our critical numbers. Still no guarantee that they are extrema, okay? They could be or they may not be, okay? So we have to test. Because there are no points for which f prime doesn't exist, you can conclude that these are the only critical numbers. Because smooth continuous, there aren't any values where the first derivative doesn't exist. We already said that 2 or 3 times or more, okay? So the table summarizes the testing of the 3 intervals determined by those 2 critical numbers. We first test anything between 0 and pi thirds. They chose pi fourths, just like you did, okay? And here we got f prime of pi fourth happened to be negative, meaning it was a decreasing function coming into pi thirds. It's 0 at pi thirds. We need to know what's going on between pi thirds and 5 pi thirds. So we didn't have to do one each. We did, but we didn't have to. we could have just picked anything here. Pi certainly worked, and if we pick there, the first derivative is increasing there, okay? And because it can't change again until it reaches that 0, you know it's increasing coming here. Oh, that decreasing here, increasing here made that a minimum, okay? We haven't made the conclusion yet, but we're making it now. And increasing here, and then past there, they chose 7 pi for us, which was perfectly fine. That would have been root 2 over 2 also, and 1/2 minus root 2 over 2 was going to be negative again, so it's going to be decreasing. That makes this value a relative maximum, that value a relative minimum. Decreasing, increasing minimum, increasing, decreasing maximum. You just need 1 point in between the two, okay? That's a conclusion about the increasing, decreasing. Let me get you here. Power, right? Okay. All right. So by applying the first root of the test, you can conclude that f has a relative minimum at the point x equal pi thirds. Yeah, we determined that. And a relative maximum at the point x equal 5/3 pi. Okay? Now, all it said is find them. Okay? It didn't say we had to evaluate them. Okay? If we were going to evaluate them, in other words, give an ordered pair, we know the x values, we don't know the y values, then you go back to the function and plug in that x in this y. It'll be a weird number, but yeah, you can determine that. Okay? So the relative minimum occurs where it changes from decreasing to increasing, relative maximum where it changes from increasing to decreasing. Okay. And that's all she wrote for that. They never did figure out the actual values of it, which seems like you would have, but they didn't. All you do is plug them into the original function. All right, now that was example 2. They're not doing example 3. They're not doing example 4. And they're not doing example 5. So let's do them. What you think? So let me do example 3 here. Find the relative extrema of f of x. And guess what? Do you think this is going to be a little more complicated than maybe the last one? I bet so. They show the simple one and don't show the more complicated one. Okay. F of x equal x squared minus 4 to the 2/3 power. X squared minus 4 to the 2/3 power. That can't be any more complicated, can it? What we're going to do first. Second? It sounds like a winner, okay? F prime of x is going to be what? Second? Yep, you got it right. So what does that produce? 2/3 times x squared minus 4 to the negative 1/3 power times, what do you say? 2x, perfect. Now, taking derivatives and that kind of stuff, I like to keep it in exponential notation. But in order to evaluate, I kind of like to go to fractional notation. Not good for taking derivatives, but it is for this part. So I'm going to rewrite this. The numerators are 2 and 2x. So that's going to be 4x. In your denominator, you have a 3 times x squared minus 4 to the 1/3 power. You moved it downstairs and lost the minus sign. Does everybody agree with that? Okay. Now, Why did you take the first derivative anyway? Because it's calculus class. That's what you always do, right? No, why? What does that do for you?
You plug in numbers into you plug into the first derivative to find the maximum.
Okay, how? What about the first derivative is going to help you find the maximum amount? Say again?
Set it equal to 0?
Yeah, either where it's equal to 0 or where it's undefined. Okay, those are the two things we look for in the first derivative. Where could it be 0 and where could it be undefined? Okay? Now, first one, where could this be equal to 0? It's the only thing that's going to make that expression equal to 0. Yeah, x equals 0. Because the only way a fractional form could be 0 if the numerator is 0, right? Doesn't matter what the denominator is, as long as it's not 0. The numerator's got to be 0 for the value to be 0. So one place is x equals 0. Okay? And that's the only place where your first derivative is 0. Now you've got to ask yourself, where might this be undefined? Anywhere? What would make that undefined? Anything? Where is a function undefined? There's only about 3 circumstances that we have for that.
You get a 0 in the denominator.
0 in the denominator is certainly one of them. Well, the 3 is in the denominator. That's not ever going to be 0, so no sweat there. Can this thing ever be 0? Where would it be 0?
2.
Second?
X equals 2.
X equal 2 for sure. Is that all? Okay. Here's what I would do. And it doesn't matter about the 1/3 power. You know, if it's a 0 in the parentheses, that's going to be 0. So what we're interested in is x squared minus 4. Is that ever equal to 0? Now, how could we solve that quadratic equation? How do we usually solve quadratic equations? What's the F word? Factor. Okay, let's see if we can factor. Can we? How? How? Does that factor? X plus 2, you said? Times x minus 2. Okay? Now, what values of x would make either of those true? Not that hard. Okay, x equal 2 or x equal negative 2. So, yeah, you got the first part correctly. And I think I know this guy. Okay. I just got to find you. There you are. Okay. Now, I was holding your name in vain earlier. They opened up summer schedule before we finished getting changes made to it. And unfortunately, the physics classes for the summer were times from last summer, but not the right times for this summer. Because every term we flip, because we have 3 terms a year, and if we have physics 201 first and 202, or 213 and 214 in one order in the fall, we flip them for the spring so that the day students can stay day students in, evening. And then we flip them again for the summer, and then flip again. Because 3 terms, they flip every time. Well, that change hadn't been put in there when they opened the schedule, and you had registered for Physics 213 in the early time frame. Unfortunately, it's moved to the late. Can you do it?
What time?
It goes till 7:20 at night. You can do that? Okay. So the same time you're having to, wait, are you at 213 or 214? 213, okay. That's because the 214 students are in 213 now, and they're in the day. And we try to always offer one section at night and keep it, we don't want the night students not to be able to come for several terms in a row. So unfortunately, you're at that phase. Okay. All right, good deal. Sorry. Shouldn't have taken class time for that, but I was afraid you'd get out before I think of it. So there's two places where that would make your denominator 0. So this is places where your first derivative would not be defined. X equal minus 2 and x equal plus 2. Okay, the rest of them, perfectly fine. So, what are we going to do? And they didn't put any limit on here, so we're going to have our number line down here, okay? And here there's x equals 0, x equal minus 1, x equal minus 2, x equal minus 3, x equal 1, x equal 2, x equal 3. I could keep on counting, but who cares? Okay. Now, we know we have an undefined slope here, so that means we have a cusp or something like that. A 0 here, slope here, okay, and then an undefined slope there. So we do the same thing as before. We evaluate the first derivative at places on either side or in between these places. So these are our, I don't know what, is my chair falling apart? Here's things, but okay. All right, this is a undefined, this is a 0, and this is an undefined, okay? So we need things on either side. What might you choose?
Can't you just do one?
Second?
One on both sides?
Okay. Want to do plus or minus 1? Okay, that certainly is going to work. So let's do f prime of, which one you want to do first? Negative 1? Okay. What is that going to be? 4 times negative 1, right? Over 3 times, what's negative 1 squared? 1 minus 4 to the 1/3 power. Now, if that had been a 1/4 power or a 1/2 power or any even denominator, all bets are off. That's another place things are undefined. You can't even go there. But at odd powers, yeah, no problem there. In fact, what's the sign of this going to be? Negative, and a cube root is also negative. And this is negative. So negative over negative is positive. So we have a plus first derivative there. Okay, Chasten's here. All right. Okay. Did you want to do positive 1 next? I thought I heard you say plus or minus 1, right?
Yes.
So it'd be 4 times 1 over 3 times 1. Oh, 1 squared is? 1 minus 4 to the 1/3 power. What sign is that going to be? We don't really care about the value. We want to know what the sign of it is. That's what? Okay, the numerator is certainly going to be positive. What about that denominator? Negative. 3 times negative is negative. So that's going to be negative over, positive over negative. That would be negative here. So we have a 0 there, increasing up to there, 0, then decreasing. That's got to be a max. Okay. Where else do we need to look? Second? Okay, we'll try 3 and negative 3. Running out of room. F prime of negative 3 would then be 4 times a negative 3 over 3 times, what's negative 3 squared? 9 minus 4 to the 1/3 power. I don't really care about the value of it. I want to know the sign of it. What do we have there?
Negative over
Negative over positive, that's going to be negative. So over here we're negative. So we're negative coming down to a -2 where we have an undefined slope, and then we're positive on the other side of it. So that basically looks like it's going to be a cusp there. Saying what kind of extrema will that be? A minimum. Okay, so this is a minimum here. Okay, now let's see what happens when we do f prime of +3. Okay, that would be 4 times 3 over 3 times, and +3 squared is also 9 minus 4 to the 1/3. What's that going to be? Positive here too. Okay, so then what do we have here? Negative coming into 2, undefined at 2, and then positive leaving 2, another minimum. Okay, I can picture what this is going to look like. I don't have any values for it, but I can still picture it. To get values for it, you just plug in the values. You could plug in your -3 here to see what value it has. -2 there, so you know what that's going to be. -2, that's going to be a 0. Okay, so this one will be right there, and +2 is going to be right there. And we know this is a minimum, so it has to be coming down to 0, and it has to be coming down to 0. That's minimum as well. Well, then we can plug in 0 here, and what is? We plug in a 0 here. This will be a -4, and the 2/3 power of a -4. You have to plug that in the calculator, but it's going to be some negative value. That's not working out very well, is it? There's some serious problems with that. That is a negative value when x equals 0. And yet we just determined it's going to be a maximum. Whoa-ho. It is a maximum. Why is my thinking wrong? X equals 0. Oh, that's it, of course. The cube root of a negative number is negative. But then when you square that, it becomes positive. And that means the squaring of a cube root. Okay. It doesn't matter which order you do it. You can square it first, and it's positive, cube root, positive, positive. Yeah, so that is positive. Okay. If that was a 1 up there, we'd have been in serious trouble. But it's a 2/3 up there, so we're all right. Okay. And there you see in the book, they don't show on the slide what that looks like. Rather strange looking thing, but you see at -2 and +2 you have undefined first derivatives, but in between that it's defined everywhere. Okay. All right. Any questions on that? Let's do example 4. Can I erase this? Okay. Let's do example 4. And this one, if you want an interactive version of this type of example, you can go to larsoncalculus.com. Here's your function. Find the relative extrema of this function, f of x is equal to x to the 4th plus 1 over x squared. Okay. Now they warn you about something before this example about it. One thing you better do on this is, and they don't give any limitations on your domain, but what the first thing you've got to do is, where is this function even defined? Or even more so, where is it not defined?
0.
At x equals 0, it's not even defined, so don't try to make x equals 0 a minimum or maximum. Because it's not even defined there. How can you have a minimum or maximum something that has no value? Okay? So, we can write down here x is not equal to 0. It cannot be equal to 0. Anything about it. Okay? Now, once we've done that, what do we do next? Take a derivative. Sounds like a capital idea. F prime of x. What would that be? What kind of rule do we use here? Yeah, unfortunately the quotient rule, not my favorite. But how does that go? Nope. It's low-D high. Okay. So it'd be x squared times the derivative of the numerator, which would be 4x cubed minus x to the fourth plus 1, the whole numerator, times, second, 2x, okay, over, yep, which is x to the fourth. Kind of a big boo hiss on this one, right? Now, I'm going to show you something in a minute that may have made life easier, but I was letting you guide the way here. But I'm going to do it now. The first term here would be 4x to the fifth minus, now you got two terms here. You got to distribute the 2x over both of the terms in there. So what's the first going to be? 2x to the fifth, and it's a minus, right? The minus changes the sign of both of those. So 2x, is that what I heard? Over x to the fourth, right? Well, what can you do in that numerator? Sort of pops out and slaps you. Not quite yet. Well, yeah, you could do that. Well, let's subtract the like terms, and that would be 2x to the fifth. You could have factored first, minus 2x. Ah, the 10 o'clock scholar. Okay. Now, Elijah, hopefully this will be good news for you. It wasn't for Jeremy. Unfortunately, they opened summer schedule before I had finished putting the changes in. So the physics class we had to change. I don't know, did you get my message? Because I left messages for both of you. I don't know if you got the phone messages. Okay. Well, maybe I couldn't leave one for you. There were a couple I couldn't leave a message. Just said unavailable. And what we do is every term we flip-flop the things because we have 3 terms and 2 classes. We always try to have, so evening students, if they take 201 in the fall, if they take 202 in the spring. Then we need evening students in summer to take 201 together. So we can have that cycle going. So that flips from every term, so we needed to flip it. So that meant you taking 214, it'll be the same time as 213 was now, or approximately 2 to 350, blah, blah, blah. So I had to make the change. Is that all right? Actually, it works out very nicely that those 2 classes are right.
I mean, I talked to you and Mr. Ryan about internship.
Oh, I see. Okay.
I mean,
Does this make it easier or harder?
Should be easier. I'll talk to you about it.
Okay. Well, there's the new schedule. Okay. I tried to call first, but then I went on and made the change before we got more students in there that I'd have to call. So there's just one each in each of the 3 classes. The 4th class, I had a student registered, but he was a transient student, so the registrar's office had to handle him. Okay. So anyway, we have 2x to the 5th minus 2x over x to the 4th. And now Clark's idea was what?
Factor out 2x.
A 2x, so that would be 2x times what's left? X to the 4th minus what? 1, got it, over x to the 4th. Well, I can do one thing here, divide out an x here and make this an x cubed here. Okay? All right. Now, that's a perfectly good form to leave it. I'm going to write it again so you can read it a little better. 2 times x to the fourth minus 1 over x cubed. Okay. Now, that was using the quotient rule, which, as we saw, first guess on it would have given us the wrong answer because, remember, whether it's low D high or high D low, that's going to change everything, right? Here's a way we could have done that first function. If we had written it this way, x to the fourth over x squared minus 1 over x squared. What would that have given us? Yeah. Isn't that what we get? X fourth over x squared minus 1 over x squared. Oh, plus 1. I'm sorry. That's a plus sign there. Have I been writing mine? No, it's fine. Okay. Right? Okay. Now, what if you'd taken a derivative? Well, what does that first term become? X squared. Plus, and then how can we write this not with fractional form? X to the minus 2. Now take a derivative of that. What does that give you? 2x minus 2, x to the minus 3. And what do we have?
You see right there where it got 2x to the fifth minus 2x over x to the fourth? Right there next to the, let's say 2x to the fifth minus 2x.
Yeah.
Because you could have just subtracted, like, subtracted the exponents. No, subtract the exponent since it's in quotient. Like 2x to the fifth over x to the fourth. Subtract the exponent.
Yeah, and that's exactly what I'm going to suggest doing now. I first got rid of one of them, but I'm going to write this in a slightly different form and write this as, I'm going to do it right here, 2x to the fourth over x cubed minus 2 over x cubed. Right? And 2x, that would be x, right? Now we have 2x minus 2x to the minus 3. You get the same result either way. Now, it's just whether you like it in this form or like it in that form or want to keep the x cubed in the denominator. I don't know. I don't care really. For calculation purposes, I think it actually is a little better to leave it as 2x minus 2 over x cubed. That's your first derivative. For calculation purposes, I kind of like that a little bit better. Okay? Now, what are the things we have to do now that we finally found our first derivative? Two different ways. See, that way avoided the quotient rule. You can't always do that, but this one you could have, and then you don't have that thing, did I do it right? Did I do my low D high or high D low? Which goes when? You know, that way would have avoided that. And you get the same answer, I think, a little easier that way. But that's me. Okay. What are we trying to find? What's our whole purpose of doing this?
Finding our critical numbers.
Yes, we want to find the critical values, okay? Critical numbers. And how would we do that? Either first derivative equals 0 or first derivative undefined, okay? Now, the only place I can see just looking at this where it's going to be undefined is where? X equals 0. But x can't be 0 anyway, right? From our first observation there, x cannot be 0. So that one's out of the picture. So we just need to find where this thing is equal to 0. Now, actually, now that I think about it, the easier thing to deal with here would be this. Let's write that over common denominator, which is sort of going backwards here. That would be 2x to the fourth minus 2 over x cubed, right? We never quite had it in that form, but we could have, okay? Yeah, we did. We could have, yeah, right there. That's this form right here. That's going to be the easiest form to evaluate. So where is this form or that form equal to 0? Where your first derivative is equal to 0. We know where it's undefined, x equals 0, but the function is not defined there. So that's not under consideration here. Where is this thing equal to 0? Yes, factor that. Okay. Does that factor? What would that be? Oh man. X squared plus 1 times x squared minus 1. Are you through factoring? No, because this x squared minus 1 will factor again, so let's leave x squared plus 1 times, what would that be? X plus 1 times x minus 1. And we want that equal to 0. Okay? If that's equal to 0, your first derivative is equal to 0, right? Well, let's see. Is x squared plus 1 ever equal to 0? Not in the real number system. In complex numbers, maybe. Yes, you can make it. Not in the real number system. Because you square any real number, it's going to be positive, add 1 to it, even more positive. 0 wouldn't be positive or negative, but add 1 to it, it still would be positive. Okay? So this doesn't contribute anything. What does this contribute? A negative 1 or a positive 1. Exactly. So those are 2 places where your first derivative is 0. Okay? All that just to get those 2 critical values. X equals 0, not an option because of that. Okay? So what I'm going to do here is erase a bunch of this. Okay? I think I will leave just this part here. That was all chicken scratch. But the form that we wound up with that first derivative was this one down here. That's going to be the most useful form, I think. Okay. And I'm also going to leave only the pertinent parts here, which yield x equal minus 1 and x equal 1. Okay? Okay. I know that's scattered all over the place, but we'll live with it, right? So, what test points do we need to use? Okay, we're picturing our number line, and x equals 0 is out of the picture. Okay? And we've got x equal minus 1 here, x equal plus 1 here. So what would be some valid test points?
0.5 or negative.
Okay, certainly 0.5, negative 0.5 and 0.5. And so you can't use 0. It's in between those, but you can't use it. It's out of the picture. Okay? And what else? How about negative 2 and 2? Yeah, that looks like winners to me. Okay? So we're going to evaluate at those 3. At your F prime. What I'm going to do is bring this up here. 2 times x fourth minus 1 over x cubed. That's, I think, the simplest form to use, so I'll erase it down here. Okay. Now, do you have a preference on which one of these we evaluate first? Pick one then. 0.5. Okay. F prime of 0.5. Okay. It's up to you which form you use that in. 0.5 to the fourth power. 0.5 squared is 0.25. Then you have 0.125, 0.0625, right? 0.0625 minus 1 over 0.125. Did I do it right? I think so. Okay. But guess what we're interested in? The value? Nah. The sign. What is the sign of this? Numerator is negative. The denominator is obviously positive. So what's the sign of this? Negative. So that means the first derivative, this is 0.5, is negative here. The first derivative, not the value of the function, first derivative is negative here. Decreasing there. Okay? Next. Second? 1, we know the first derivative is 0, right? Already established that. So the first derivative is 0 here. First derivative. And what next? 2. Okay, let's do 2. Y'all like positive numbers, don't you? So f prime of 2 would be 2 times, and what's 2 to the fourth? 16 minus 1 over 2 to the third is 8. I really don't care about the value. All I'm interested in is the sign. Okay? What's the sign of that? Positive. Okay? So at 2, we have a positive first derivative. So that means you're coming down here, I don't know where, but decreasing slope, 0, and increasing slope. That's probably not drawn right, but that's the general shape of it. Okay? All right? Got 2 more. Because we know the first derivative here is 0. Okay? Negative 0.5. So f prime of negative 0.5 would then be 2 times, and negative 0.5 raised to the fourth power is still 0.0625, right? Minus 1 over, but negative 0.5 cubed is negative 0.125, right? Cube a negative number. Any odd power, negative number raised to an odd power is negative. A negative number to an even power is positive. Okay? So what's the sign of the numerator? Negative. What's the sign of the denominator? Negative. What does that make the sign of your first derivative? Positive. So here we've got a positive slope. Okay? How about negative 2? F prime of negative 2. That would be 2 times, and negative 2 to the fourth power is 16 minus 1 over, and negative 2 to the third power would be negative 8. So what's our sign at x equal negative 2? Negative. Positive in the numerator, negative in the denominator, that's going to be negative. So what have we got here? Coming down to a 0 and going up again. Well, that's obviously not it, but that's the general shape. So both of those are relative. They're both extrema. Got that. Men, both of them are relative minima. Okay? Okay. They show pictures in the book, and sure enough, they actually do the evaluation there. Because it's fairly easy to plug those values in. At negative 1, in your function form, you get 1 plus 1 is 2 over 1 is 2. So negative 1, 2. And at positive 1, it's 2. So those are your 2 values there. No value at x equals 0, even though your first derivative is undefined there, because the function's undefined there. You can't do anything about that. Okay. Any questions on that? Now, can I erase it? Okay. Now we have a little more practical problem here. The path of a parabola, of a projectile. Neglecting air resistance, the path of a projectile that is propelled at an angle of theta is y is equal to negative g times secant squared theta over 2 v naught squared. All that is times x squared plus, oh, I love this one, tangent theta times x plus h. Okay? Now this is only good for theta in between 0 less than or equal to theta less than or equal to pi halves. Okay. Now, we're picturing this, or at least they did in the book, as shooting a basketball. Okay? Or throwing a baseball. Okay? Or football. Hitting a tennis ball. Hitting a baseball. Everything follows parabolic paths. That question of air resistance, you a big curveball pitcher? No, fastball. Okay. You don't care if it's moderating or not. Okay. You like to have movement though? Yeah, okay, yeah. So a little bit better. Okay. Now, here your variable is what x, not theta. Pick a theta, any theta, and then this will be your function in x. Okay? Now, why do they limit that to between 0 and 2 pi? Okay? When Harrison is throwing his pitches, an angle of 0 is going to be here. Anything he throws below that, his catcher is going to be fussing at, right? Because it's bound to hit the dirt before it gets to the catcher. And it's a question of a pass ball or wild pitch, right? Okay. If it hits the ground before it gets to him, it's probably going to be a wild pitch, isn't it? Probably. Okay. So we don't want anything that's less than 0. But neither is he going to have an angle up here, okay, because that ball is going to go straight up and come back straight down. And meanwhile, they'll be stealing bases on him like crazy, especially if he throws really hard. So we don't want that to happen either. So it's going to stay between 0 and pi halves. So this is a practical thing. I mean, you don't fire projectiles behind you, you know, in general, you know, unless you're running real fast. And, you know, yeah, we don't usually do that either. Okay. And you don't do, firing into the ground isn't making a lot of sense either. Okay. So that's why that limitation's there. All right. Now, what are we asked to do here? Neglecting air resistance, the path of a projectile that is projected at an angle theta is this formula, where y is the height, x is the horizontal distance, g is the g. What is g? Acceleration due to gravity, okay? V0 is the initial velocity, and h is your initial height. So, what that means, if you're shooting a basketball, a set shot, that might be coming from about 5 feet if you're shooting from here. Jump shot from up here, it may actually be quite a bit higher, okay? Harrison's pitches, I don't know where you usually release from, over the top or vary or where? Huh?
Over the top.
Over the top. So it'll probably be something greater than 6 feet, right? That would be his h, okay? So that's your initial height, okay? This equation is derived in section 12.3, so go back there and look at it if you're really all that interested. We're going to let g be 32 feet per second, which puts us in the U.S. customary frame of measurement where you're dealing with feet, not meters, okay? So we're going to use feet per second squared. V0 will be, of course we need that also, 24 feet per second. That's a pretty rapid rate of speed, isn't it? 24 feet in a second. And the initial height is 9 feet. Boy, that is a good jumper, isn't he? He must be a tall dude, okay? And has springs in his feet, okay? What value of theta will produce the maximum horizontal distance? Horizontal distance. So we're trying to maximize our x, not your y, okay? Interesting, okay? All right. Now I said that your theta was fixed, but that's not it. That's a variable here, okay? Now, your maximum horizontal distance. If I were to draw a picture of this, and I draw pretty ugly pictures, as you have already determined, okay, and this guy is shooting, say, the basketball, and he's jumped pretty far up there. Well, let's see, his hands are like this, you know, shooting the basketball from 9 feet high. The maximum horizontal distance, and most basketball courts, hopefully, are flat, right? Okay, you don't like them to be going up or down hills. I played on some that sort of did. Okay, so maximum horizontal distance, x, that's going to be what you're looking for, x max. Well, guess what? On a basketball court, the maximum horizontal distance is going to be when it hits the ground. What's your y there? 0, right? Because he's shooting from 9 feet up, but maximum horizontal distance would be, the first bounce would be, and y is equal to 0. So therefore, we can take the y out of the picture here and have a function of x's and thetas only. Okay? So here is our equation, minus g, and that's just a number, by the way, so that's not a variable, secant squared theta over 2 V0. Oh, did they give us that? Yeah, V0. G is 32 feet per second squared. V0 is 24 feet per second. H is 9 feet. What will be the value? So let's plug everything in we can plug in that we do know already. So the G we're going to put as, the V0 we're going to put as, okay, 32. We're going to leave off the units now. I hate to do that, but it just will mess up the problem. 2 times, it was 24 squared. Okay, going to be sort of a big number there. Okay, times x squared plus tangent theta times x. I would say x tangent theta, but they do it that way. Plus 9. Okay. And that's going to be equal to 0. How are we going to maximize your horizontal distance? What we have now is horizontal distance as a function of theta, right? So you have theta really short, probably it's not going to go that far. Higher, go up further. Too high though, horizontal distance gets too short again, right? So we're trying to maximize the theta with this formula. I can make a guess right now, but I won't do it. Okay? Second? That's what I would guess. Okay. But let's see. How would we do this? Now, at some point, you've got to square 24, multiply it by 2, and minus 32 over that. It's going to give you a rather weird number. So let's go and get that out of the way. Negative 32 over 2 times 24 squared. What does that give you? We can make it a little easier, can't we? That would be 2 into 32 will be 16. 24 is 4 times 6 times another 4 times 6. And 4 times 4 is 16. So that wipes that out. So it's minus 1 over 36. Is that right? I think I did it right, but I may have messed up.
24 squared over 576.
Okay. So 32 divided by twice whatever you just said. What's that?
I was just saying, secant is
Oh, don't worry about secant. Just the number. Minus 32 over 2 times 24 squared.
oh, that's minus 32 over 1152.
Over what?
Over 1152.
1152. Now, and do a reciprocal of that and see what you get. If you get 36, you're fine. Or I'm fine.
Oh, yes, sir.
Okay, yeah. So it's negative 136 secant squared theta x squared plus tangent theta x plus 9 equals 0. Okay. Now, what have we got to do with this? What we're trying to do is maximize the x, so that becomes the dependent variable as a function of theta, the independent variable. So how are we going to do this? We're trying to get an extreme of what do you do? Take a derivative with respect to what? Yeah, y's out of the picture here, okay? So it's x's and thetas. You want derivative of x with respect to theta. So this is going to be the independent variable. That's your dependent variable, okay? So what you got to do, but here they're all mixed up in here. So how are we going to do this? Oh, several sections ago, wasn't it? Forgotten that. Maybe even last chapter, was it?
What was that chapter?
Say again?
2.5.
2.5, what was it? What you dealing with?
When you're trying to get the derivative by itself.
Right. It's called, say again? Implicit differentiation. There's the term we're looking for. So what are we going to have to do here? Look. Okay, well, okay, it's going to be x prime, where x prime is dx d theta. That's what we're looking for, is x prime. Okay, but this is your dx d theta. So the minus 1 over 36, or you could put a decimal there if you prefer that. Okay, and there we have a product rule, so that would be what? Derivative of this would be 2 secant theta times the derivative of secant theta, which is secant theta tangent theta. So that would be secant squared tangent theta, okay, times x squared, because the product rule says the derivative of the first times the second, okay, plus the first secant squared theta times the derivative of x squared, which is 2x, but then you do your x prime. Very good. That's your dependent variable, so that's what you need. Okay, plus another product rule here. What would that one be? What you going to do first? I don't care much. For this term, what's its derivative? Squared. So it'd be secant squared theta times x times, or plus, tangent theta x prime, right? Because it's derivative of x, okay, equals 0. Yeah, got that part right. Oh my goodness. All right. Now, I can't believe they're giving you this problem. This is really a pain in the neck problem. And they choose a way to do it, which I find to be rather bizarre, but it's okay. They use the quadratic formula right off the top. Wait a minute. They just start with this. They haven't taken a derivative yet. And they, goodness gracious, what are they doing? They're not taking a single derivative, okay? They're just monkeying around with the quadratic formula here. I would say rather than waste or spend any more time on this problem, read it in the book. I'm trying to find the rationale for this. They come up with this equation, and then they solve for x. And at this point, you need to find the value of theta that produces the maximum value of x. Oh, and there they do the first derivative then. By hand would be very tedious. Using technology to solve the equation, however, eliminates most of the messy computation. The result is this. Okay, that's how they did it. Okay. They didn't do what we were trying to do, which was first derivative test. Or that's what I was suggesting you do. It really, I hope to say this, isn't all that bad, okay? Because you notice here, every place you have a secant is secant squared. And using a Pythagorean identity, you can get that in terms of tangent squares. And then, and that's what I was going to do, but that's when I stopped and said, I can't believe they're asking you to do this. But you could do that and get all those in tangent squares, and then separate your x prime from your x's and that kind of stuff, and set it equal to 0. So you could do it, but they avoided all that. That's why I said, I can't believe that they're asking you to do this. And they said, and that's why I had to stop and read, using technology to solve this. In other words, you get a package to do your first derivative for you, and you came up with this. Well, give us the package and we'll do that. I mean, why put the problem in the book? Sorry about that. I'm liking this author a little bit less now, but you know, you can get the technology. So anyway, that finishes 3.3. Homework exercises. Do number 3, okay? Just using the graph, pretty good thing to look at, and do. The answer is found at calcchat.com, not at calcview. Then do any of the odds 5 through 9. All 3 of those are at calcchat. Number 5 is at calcview. Do any of the odds 11 through 17. All of those are at calcchat. 13 is at calcview. Do any of the odds 19 to 39. They're all at calcchat, but only 21 is at calcview. Then do any of the odds 41 to 47. All four of those are at Calc Chat. 41's at Calc View. Then do any of the odds 49 to 53. They're all at Calc Chat. None of them are at Calc View. Do 55. Another quotient rule, it looks like. Okay. Then do any of the odds 57 through 62. And all those last ones are at Calc Chat, not at Calc View. And then there's an exploring concepts, transforming functions, which we haven't really done before. If you want to look into that, 63 or 65, 67 or 69, you don't have to do those unless you just really feel a need to do so. Analyzing a critical number is number 71. That's probably not a bad idea to think through anyway. 73 is another think about it type problem. See what that tells you. 75 is a reasonable problem to look at, I think. 77, perhaps too. All these should be at Calc Chat. And 79. Any of you going into a medical field? You are. 79 is a trachea contraction type thing. What are you, bioengineering?
Pharmacy.
Oh, pharmacy. Okay, you may not be that interested in that then. Okay. Motion along a line, that is something you'll hit in physics, so 81 or 83 would be good problems to do. 85 probably also a pretty good one to look at. Wow, they have enough of them in here, don't they? Creating polynomial functions, 87 or 89, that's going the other direction. And then you got some true false there, 91 to 95. No, 91 to 95. And then you've got a couple proofs, 97 and 99. So the main ones are the things up to, I would say, 61. The others, take a look at. I think 81 and 83 are pretty important too, so you might want to take a look at those. Now, how are we on time? Oh, we got a few minutes. Let's go now. We had run out of slides forever here, so let's at least get started in 3-4. Won't have time to do much, but at least get started in it. Okay. Chapter 3, application of differentiation. We just had the guy shooting the basketball. 3.4 is dealing with concavity and the second derivative test. What does the first derivative tell you about a function? Say again?
Slope.
Okay.
Slope.
Okay, it tells you about the slope. And what is that telling you? It's telling you how the function is changing with respect to the independent variable. If the slope is positive, that means it's an increasing function. If the slope is negative, that means temporarily it's paused there, not increasing or decreasing. If it's a negative slope, it means it's decreasing. Yeah. So it tells you about how the function is changing. So what do you reckon the second derivative is doing? Maybe telling you how the first derivative is changing. Because that's what you do. You take the first derivative and take another derivative, right? So the second derivative tells you how the first derivative is changing. Is it increasing? Is it stopped? Is it decreasing? Or what's it doing? Okay? That's what the second derivative tells us. So that leads to a concept called concavity. We haven't defined it yet. We will. But that's what the second derivative is going to do. So what we're going to do here, the objectives in this section, determine the intervals on which a function is concave up or concave down. The shape of the graph is it concave up or concave down. Okay? find any points of inflection of the graph of the function. Now, what is a point of inflection? Where the concavity changes. Okay? So if it's concave up here, and down here, and up here, someplace in here, the second derivative is 0. The first derivative isn't necessarily, but the second, that's going to be a point of inflection. We'll apply the second derivative test, which we haven't defined yet, to find the relative extrema of a function, and you'll find that's much easier than evaluating a derivative on the left, on the right, and in between, and that kind of stuff. So this is giving you an easier way to do what we were just doing. So let's first talk about concavity. Okay? Now, I can remember when the first time I ran into this term was in a physics class. And with lenses or mirrors, let's talk about mirrors, say. If a mirror was shaped like this, and you were looking at it, we called that a convex mirror. If it was shaped like this and you were looking at it, we called it a concave mirror. And I can't remember who it was I was taking that under. They said it looks like the mouth of a cave. So that's where concave came from. So that's what concavity is, where the thing. This is concave down, this is concave up, because the cave is facing that direction. Okay. So we've seen that by locating at intervals on which a function f increases or decreasing helps you describe the graph. In this section, we'll see how locating intervals over which f prime is increasing or decreasing. Tells how a function is increasing, we take the first derivative. How f prime is increasing or decreasing, you take a second derivative. Take the derivative of the derivative. Okay? To determine whether the graph is curving up or curving down. So here's the definition of concavity. Let f be a differentiable function on an open interval I. Okay? The graph of f is concave upward on I, where f prime is increasing on the interval. Okay, now what does that mean? F prime is increasing. Now we know what it means for f prime to be positive. That means the function is increasing. But for f prime to be increasing, that would mean if the slope here was slightly positive, for f prime to be increasing, the slope would be getting more positive all along, right? But even if the slope was very negative, if it's getting less negative as you go, that first derivative is increasing because it's going from a very negative number to a less negative number, so it's increasing. So you see all along that path, you've got a concave up situation. Okay? So that's what we mean if the f prime is increasing on that interval. It's concave downward on I, where f prime is decreasing on the interval. So give me a value for f prime, positive or negative?
Negative.
Negative. Really negative or slightly negative?
Really negative.
Really negative. Okay, coming like this. Okay? He's already starting really very small, very negative f prime. Okay? For that to be decreasing, it has to get more and more negative, doesn't it? Woo! Started with a tough situation there. Okay? Because it was already really negative and it has to be getting more negative. Well, sure enough, that would be concave down. Okay? So let's not go quite so negative. Okay? What do you want f prime to be?
Positive.
Positive. Really positive or slightly positive? Slightly. Slightly positive here, and if it's decreasing, then in a while it's going to be 0. Right? And then it'll be negative and more negative and more negative. Sure enough, that's concave down. And if you started very positive, and you got less and less and less and less, and then 0, and then more and more, concave down. So that's what concavity is. When the first derivative is increasing, you're concave upward. When the first derivative is decreasing, concave downward. And how do you find whether it's increasing or decreasing? Take the second derivative, okay, and see what happens, okay? All right. The following graphical interpretation of concavity is useful, at least that's what I was waving my arms about. Sorry, folks listening at home, you can't see my arm waving, okay? Too bad. Be here. Hello, okay. Let f be differentiable on some open interval I. If the graph of f is concave upward on I, then the graph of I lies above all its tangent lines. I don't think I ever would have thought of saying that, but that sure is a good way to express it. The graph is always above. Here's a tangent line here, here's a tangent line, there's a tangent line, here's a tangent line. Everywhere the graph is actually above the tangent line. That means it's concave upward. Alpha prime is increasing. I'm not sure that's it's certainly true. I don't know how useful it is, but it's true. Absolutely true. Okay? Let f be differentiable on the alpha interval. If the graph of f is concave downward on I, then the graph of I lies below all its tangent lines, always below it. That means it's concave downward. Yeah, maybe I'll start thinking in those terms before. I never would have thought of that before. But it's fine. Okay? So I think that's just about run us out of time. So we'll begin next time near the bottom of page 191. We didn't get far enough along for you to do any homework exercises there. We'll move on with contact. Good deal. Any questions?
Break, right?
Oh, shucks, that's true, isn't it? Good news, bad news situation. The good news is next week is spring break, but the bad news is we won't see each other then, will we? All right, get over it. All right, good deal. Have a good spring break, everybody.
You too.
Don't worry. I'm planning to. Yes.
Are any of those physics classes offered on Monday and Wednesday?
Yeah, they're all Monday, Wednesday.
Okay, because I wasn't able, I was just looking before class and I wasn't able to get into linear algebra because.
It's Tuesday, Thursday.
Yes, sir. I have to stay on either have to be on Tuesdays, Thursdays, or Mondays, Wednesdays because of my job.
Yeah. Yeah, the calculus and physics are on Monday, Wednesday, and then the other courses I teach are on Tuesday, Thursday. Yeah.
Okay, that's what I'll shoot for.
What's that?
Well, I was just saying that's what I'll try to get in this space.
Yeah.
And I've never had a physics class before, and this is not Physics 100.
No, are you a pre-engineering? Okay. I'm guessing you need 213, right?
I know I need the first one.
Okay, yeah, well, there's 201 and 202 are trig-based physics, and 213 and 214 are calculus-based physics. And I'm guessing pre-engineering, most of them require the calculus-based. They call that, the other they call college physics, and the ones that are calculus-based they call physics for science and engineers. So usually that's the one that the pre-engineering students would take.
Well, do you think I'll be all right?
Yeah, this course is your prerequisite for Physics 213.
Okay.
So yeah, you'll be fine.
Yes, sir.
And Dr. Bryant, if he's the one listed to teach it, he's really good. Yeah, I think you'll like it.
Yes, sir.
And I'm trying to think what time. Let me see. I can tell here.
I think Calculus 2 was from 11.
Okay, it's late in the evening. It's I think his starts at 4 to 5:30, and then 5:30 to 7:20.
Is there another one that I could possibly take? It's earlier than that because I work evenings.
Oh, you do? No, that's the trouble. We had to, we flip them that way so we can always accommodate evening students for 2 consecutive terms, and then day students, and then flip them so that the others get.
Well, do you think it would benefit me to take the 213?
You have to at some point if you're going into engineering. What you could do.
Well, I mean, not the 213, but I mean college physics.
It's the same times. You see, we match them up that way. What you could do. I record every class. If you wanted to take the linear algebra, if you just need something to take, you could take it even though. And just try to follow it on the YouTube videos. That would be another option.
Yes.
So, or check with Dr. Bryant. He may work with you on it if you follow it. He doesn't record everything. He has his labs out there, and he puts a lot on Blackboard. So it may be possible to do it.
Yeah, because I know that's how y'all said y'all was gonna do me since I was doing this internship.
You what?
I said, I know that's how you said you was gonna do me with the internship.
Oh, I see, yeah. So he'll be doing the same type thing. Yeah, well, he'll be doing it with calculus and physics. Okay.
Yeah, well, I feel better.
Yeah. Did you have something for me, or you just? Oh.
That's actually what I was going to ask you about.
Oh, I see.
I know you told me earlier.
Yeah.
So I just wanted to remind.
Right. That okay? Of what? Just the fact you're going to be doing the internship. Yeah.
Yeah.
Yeah. You talked with Dr. Bryant.
Yeah.
Yeah, and he's okay.
Okay.
Yeah. You know, I record everything, so you can follow. It's all up to you.
The attendance.
Huh?
It's just like how would you record attendance for me?
What I have people doing now is completely up to you. They'll email me or give me a call or something like that. And if I've heard from them, then I mark them as present that either the previous day or the next day, whichever is closer. If I haven't put attendance in already, I do it the previous day. If I've already put it in, I'll mark them present for the next day.
Okay.
Yeah.
Yes, sir.
Uh-huh.